Okay, hello everyone. How was your weekend? Good. Lecture 16 is on a topic I like to call little, medium, and big data to try to understand what big data means and what it doesn't mean, and to help you to be able to talk about different sizes of data in an intelligent way, which is different than I think what most people can do. But before we get onto that, I want to talk about just review last lecture where we talked about number representations, and basically this is like distinguishing between the different ways computers store numbers, which are different binary encodings of numbers. The most basic format for storing data numbers that you might find is just as text, where it's equivalent to like typing in the number. So you have different characters and like periods and whatnot to represent decimal numbers, base 10 numbers. And a lot of times you'll import data in those formats from like CSV and JSON files. But then when you actually do processing, generally you have to convert from a decimal number to some kind of binary representation. And you may not even be aware that this is happening. So it's useful to understand what is happening, because there are a few things that can go wrong and a few kind of weird results you can get due to the underlying number representations. The two basic representations that we saw were integers for representing whole numbers, and there you have to keep in mind that like a 32-bit integer can only go up to 4 billion or 2 billion if you have signed numbers. So you sometimes need 64-bit numbers, and sometimes you have a choice between 64-bit and 32-bit numbers that have different maximum sizes. Integers are useful for counting and identifying records. Cases where you don't need to have fractional numbers, and actually it might be harmful to have fractional numbers. On the other hand, floating point numbers are a binary scientific notation representation of numbers, which allow you to store really huge numbers and small, tiny fractional numbers, because you have both some significant figures in the mantissa, and also some exponent for the times 2 to the something part of the scientific notation, which allows the number to get really big or really tiny. And so floating point numbers are useful for measurements and calculations because of the ability to store huge and small numbers and to store fractional quantities. But they're not always better than integer, because there's a trade-off in the sort of like precision. So you can only store, you have fewer significant figures in floating point as you do it with an integer representation, because you're taking a bunch of bits and devoting them to the exponent. And then within floating point, you again have a choice between a 32-bit and a 64-bit value, which is called signal and double precision, which gives you more or less precision. And fixed point was kind of an in-between thing, where you actually use integers to represent fractional quantities by representing them in terms of the number of fractions. Like you had a fixed fractional quantity, like you could represent dollars and the prices with the number of cents, which is an integer quantity. And then with floating point, we saw that catastrophic cancellation can happen with subtraction, leading to results where you have very little significant figures, even though you wouldn't have expected that. And that was, I think, a little bit confusing because there weren't great examples for it. But rather than diving more into that, I'm going to move on to a new topic, which I hope will more readily capture your interest, which is big data. Okay. So you've all heard of big data, right? So can anyone tell me what big data is? Okay, maybe not. I think even if you asked an expert what big data was, you'd get different answers, because the term is used like kind of fast and loose, and everyone wants to position themselves as a big data expert and have big data tools and be doing big data analysis, because that's the cool thing to do. That's the new thing, right? But in general, I would say big data is analysis and data sets that involve more than just one machine. When I say machine, that's like, computer science jargon for a computer. So you have more than one computer that is storing the data and also doing the processing. That kind of falls under big data. So the reason, in the old days, we didn't really do that because we didn't really have huge data sets, because there wasn't like all this stuff happening on the internet, and there weren't all these measurements going on and collection and storage of stuff, and people didn't realize they could make money off of like tracking consumer behavior and stuff like that. They kind of did, but they didn't have the tools to do it. So if you only have one computer, you have one CPU, which means it's like the processor on a computer. That one computer has limited input-output capacity, so I/O, meaning the number of things it can read and write at once, because there are only a certain number of electrical connections it has to the outside world. It only has a certain amount of memory, like a limited amount of capacity for storing stuff temporarily. It also has a limited number of probably disks that are connected to it. And each single computer has a limited processing capacity, the amount of calculations it can do per second. Although this third thing is usually not the bottleneck, because actually a single computer can actually do a surprising amount of math in a second or whatever. But more importantly, there's a limited amount that you can transfer in and out of the computer. So obviously, and intuitively we know that a single computer has its limits. Once you reach those limits, then you need to use many computers at the same time somehow to solve your problem. And that's all well and good, but it actually becomes a lot more difficult to use multiple machines. So coordinating multiple machines is very difficult, even if you're just hopefully you would imagine that maybe there's some magical system that others would build that would do all that coordination for you, and then as a user you could just write your SQL query or whatever, and somehow the big data system would run it. And there are such systems being built and whatnot, but in general we'll see a little bit in this lecture, how distributed systems, parallel systems, big data systems can handle more data, but have some drawbacks compared to traditional single machine kind of systems. Okay. So the general idea of distributing a database is what we're talking about in this lecture. So I know that in your homework you've downloaded a SQLite file and run it on your computer. And in the latest homework, you've connected to a MySQL database remotely, which is a big computer somewhere in, I don't know maybe it's in tech. But it's still one computer, even though all of you are accessing that one Murphy computer for the Yelp and Stack Overflow databases. It's still one computer. It's a big computer, but it's one computer. If you wanted to do more stuff at once with more data, you want to have lots of computers together working together. So here you have a lot of computers connected to a switch, which is a networking device, and somehow they all store pieces of the data and they communicate with each other and they share data to get the analysis done. Okay, and we'll talk about a couple different ways of how that sharing works to give you an idea of how these big data analyses work. So we call these different computers nodes, and the whole thing together is a cluster. So we have a cluster composed of nodes, and you are doing your work in the cluster, but somehow the cluster needs to orchestrate the division of labor among the nodes, right? And I'm going to start off talking about distributed databases, because I think this is the simplest form of big data that we can understand. This includes things like MongoDB, which you may have heard of. There's also Cassandra, Amazon DynamoDB. DynamoDB was maybe one of the first of these that was invented and documented, which inspired some of the other ones. But this is also similar to distributed file systems. So storing data in a database is kind of the same as creating files, because it's data that lives on. You can access it if you know what it's called, kind of. So distributed file systems like Hadoop HDFS, Google File System, which have had several different versions over the years, Amazon S3, those are all file systems that are not just on one disk. If you have a USB stick, there's a file system on it that allows you to store files on that USB stick. If your computer has a hard drive and it has a file system that lets you store files on that disk. A distributed file system is the same abstraction, it's a bunch of folders with files in it, but it is stored not on one device, but across many devices. Okay, and the technology behind it is similar to a distributed database. Okay, any questions about just the basic ideas so far? Before we go on, all right. So when we move to a distributed database, we actually haven't talked too much even about how a traditional database is implemented. So, so if you're moving to a distributed database and trying to implement such a thing, there are a lot of additional challenges such as, so we're not going to actually go into details of just how these are implemented, but at a high enough level for you to understand what the benefits are and trade-offs. So you have to somehow balance the storage and processing. So if you want to store something, it has to be, you have to find a place to store it among the many different possibilities, many different nodes. If you want to do some work, you have to choose a node among the many different nodes. You have to find data somehow. So it's no longer, with a traditional database, you know that all the tables are in one computer, and you check that computer to find, you run the query on that one computer, and the database engine somehow finds it within its storage. But if you have many different nodes, you have to somehow figure out which of the nodes, you have to find some subset of the nodes to ask for the data. You don't want to ask everyone for the data every time. Like if you have 8 different nodes and every time you do a query, you ask all 8 of them for that data, for a little bit of data, that defeats the whole purpose of having a distributed system, because if every node is involved in every query, then you might as well just have one node. Like that, every node has to be fast enough to handle all of the data, all the queries across the whole system, which would be a problem. I mean, the whole reason we moved to having many machines is because a single machine wasn't capable of handling the whole load, right? So we have to somehow have a scheme for finding data that doesn't involve asking everyone each time, but somehow magically finding just a few of the nodes that have the data we need. So we need a scalable distribution of data and analysis. We can't have one node do all the work. We can't have any one node that's involved in all of the work. We also want to have fault tolerance, because it's more important to have fault tolerance, because if we have dozens or hundreds of nodes, there's more likelihood that any one of them will fail, right? Like if you have if you have a system that has 99% reliability, but then that's great. But then if you're relying on 100 of those systems to function correctly at a given time, then each one of those can't fail. So you have to multiply the probabilities, so your overall system reliability goes way down, right? So at a big technology company like say Google or Amazon, they have computers crash every hour, and they have to tolerate that without because they have so many computers, it's just bound to happen, right? And similar, because another challenge is that because we have many different nodes storing data, it would be possible for different nodes to have contradictory information about the same entry, the same record, but we don't want that to be the case. So when things change, in other words, those changes have to be applied to all the different places where the data is stored, if there are replicas of data. All right. So the basic technology or the concept behind distributed databases is actually hashing. Has anyone seen hashing before? Has anyone taken 214 by chance, CS 214? Okay, I doubt it. Yeah, so hashing is kind of important in computer science, but it's a pretty simple idea. So a hash is an algorithm that takes a value and returns some kind of random value from it. And it does it so it's kind of a random output, but it's consistent and it deterministic. So you give it a value, and it returns some random looking value, but it's not truly random. If you give it the same value again, like here I have Steve with a capital S, I gave it Steve again with a capital S, and it outputted the same value again. If I changed it from these first two are different because one's capital S, one's lowercase s, so technically the bits are different. So that small change in the input led to a totally different output. And then, different other inputs give totally different other outputs. And the inputs could have different size. Like this file here, taleoftwocities.txt, has 80,000 characters, and it also gave an output of the similar size, but it's just a different value. Okay, so a hash is a function or an algorithm that takes some inputs and does something to it and gives an output that looks kind of random, but it's not random in the sense that it always gives the same output for the same input. All right. So these are actually really powerful. We'll kind of see why. And there are standard hash functions. So this here is actually an example of using the MD5 hash function, which is a standard one. If you like open up your Mac and go to the command line, you could type MD5, and that would be a command you could run on a file to give you the MD5 hash of that file. So it would read through all the data, run it through this function, and give you whatever the correct random value, not pseudo-random, but the correct hash of that value is. So what is a hash function? It's just some function that takes an input and produces an output that seems kind of arbitrary, but it's consistent for the same input, gives the same output. So, for example, if we have the numbers 0 through 99, we want to hash them. Or sorry, if we're dealing with text and we want to map to the numbers 0 through 99, we need a hash function would output some number between 0 and 99 for every input in some way that's consistent, but somehow like pseudo-random. So you could take the length of the string and modulo 100, meaning that like once you divide by 100 and take the remainder. You could take the first letter in the text and look at the ASCII encoding of it, and again divide by 100 to make sure it's within this range. You could count the number of ones in the binary representation of the text, and then divide by 100 and take the remainder. So if there were 994 ones in the input, then the output would be 94. And you could do something more complicated, like multiply the length of the string by the ASCII encoding of the first letter in the text and subtract the ASCII encoding of the last letter in the text. So basically, my point is that these are a bunch of rules. Like these are all deterministic. You could code these out. These are functions you can apply to input text that would give you some output. It would be the same every time you ran it on the same text, but it's doing something kind of arbitrary. And the point is just to output some number, in this case between 0 and 99. And some of these are good hash functions, some of them are not. A good hash function would be well balanced between these different, the output range, and it would be sort of pseudo-random so that if you change the input slightly, it gives you a totally different output. And there are specific functions that have been carefully designed by cryptographers like MD5 and SHA-1, which do this. I mean, they can't be described as simply as these hash functions are defined, but they have some rules. Like the SHA-1 hash function, which is the most popular one, it takes a bunch of bits, like breaks it into chunks, and then it performs different operations on the different chunks. And like sort of like this is a stage of it that transforms each of the different parts in a different way and shifts it over, and then repeats it again and again a few times. So details are not really important, but it's like a set of well-defined operations that take on the input that lead to some output that is somehow pseudo-random. But random, I'm using that word random in a very peculiar way here, meaning it's deterministic. Like the rules are set, so you know that if you apply the rules, you'll get the same thing each time you run it on the same input. But it's hard to predict what the output's going to be, is what I mean by pseudo-random. Okay. So does that definition of hashing make sense? So if you bring up the terminal on Mac, I believe there's a MD5 command, and you can give an input like hello, put it into MD5, and it gives an output. Okay, so this is an example of using the MD5 function, and if I change it from hello to hello period, I get a different value output, which is totally different. And if I change it from hello period to hello comma, I get yet another output value, which is again totally different. Okay, and I can give it really long inputs, and it'll still give me an output that has the same size. So it's basically choosing some value in some really large range. Like this is, I don't know, 128 bits maybe, or I don't know exactly what it is, but if I give it the same thing again and again, it always, for the same input value, it always gives me the same output because it's following the same rules each time. It's just that it's hard to tell what the rules are going to be. It's hard to reverse in particular. So given if you gave me this output I would have trouble figuring out what the input was that led to it, because it's kind of scrambles up the input in a weird way with a bunch of steps that is hard to like really, that doesn't really have any clear meaning. Question?
Yeah, I think what I was trying to think of is the utility of this.
Yeah, yeah, that's a good point. We'll come to it, but just like assume there's going to be the utility will be clear actually in a few slides, but just understanding what it does. Okay, let me give you Let me give you an easy to understand use case for this, which has nothing to do with what we're talking about in class. But let's say you downloaded a big file from the internet. It was like 5 gigabytes long, so it took you like an hour to download this file, and you wanted to make sure that that it wasn't corrupted when you were downloading it. So in other words, you want to make sure that your copy of the file is the same as the copy that was on the server or that your friend has. So you could take the file and like spit it out. You could run it through this thing, and it would give you like some value like this. And a lot of some websites that like host important files, like if you're downloading like the Linux operating system or something from an official source, a lot of times on their website they'll say, okay, here's a link to the file, and here's the MD5 sum of the file, so that after you download it, you can run this thing to make sure that you actually like no little change happened during the download that screwed it up. Okay, that's one use case. That's not exactly what we're doing in this class with it. Yeah. It works on any input data. So it could be any file, absolutely. It could be, like what do I have here? So here I have this file, xv6.image. It's like a disk image for another class I'm teaching. I could put that into MD5. It gives me something. So cat is just the command line tool on Unix for printing out the contents of a file. I could look at this new file, that text, put that into MD5. It gives me something. These are all, and every time I've run this MD5 on a different input, it's given me some other different number, which is in some huge range. So this is a hexadecimal number with a lot of digits, right? So it's very unlikely that if I run this on 2 different inputs, I'll get the same output, because this is a well-defined hash function that's meant to be pseudo-random. But if I run it on the same thing twice, I get the same output. Okay? Any other questions about hashing? Okay, but the question remains, like, why is this useful? I've given a motivation for, like, okay, if you want to verify, if you want a short summary of the data, a hash gives you that. That's useful for checking to see whether 2 copies are the same. I mean, it's theoretically possible that you downloaded the file and the change was made in some way that led to the same output, because technically there could be a collision, meaning that like you get the same output for different inputs, and because the number of inputs is different than the number of outputs, you know for a fact that there's an infinite number of inputs that lead to the same output. But the chances are very low. The chances are just infinitesimally low that any particular corruption of the file would lead to the same output. Okay, cool with that? All right, so that's hashing. It's kind of a cool idea. And okay, so let me give you a little bit of a computer science data structures lesson here that motivates hashing. So if we want to store things, like let's say rows in a database in some big array, some big structure that has a lot of slots, we want to do that in such a way that we can quickly find the thing we're looking for without having to scan through the whole list. Then we can use hashing to solve that problem. So in this case, so hash table does that. So let me see, do I have? Okay. So a hash table stores a key and a value pair. So this is the abstract data type for this is called a dictionary or a map. So like if you've used Python, a Python dictionary is an example of it's something that could be implemented with a hash table. But it's like you have a key and you have a value. You want to store these things in this table, and you want to be able to retrieve them later using the key. So, for example, you could store a word and its definition, which is kind of why the term dictionary is used as one of the terms for this abstract data type. Whoops. So you could have a list of English words and their definitions. Those could be stored in the table, or it could be like you have a table in a database, and every record, you want to store every record, and the primary key is the key, and the value is like the list of all the column values. Either way, you can think of those as keys and values. To find the data, you supply the key, and somehow that gives you the value. Yeah. So to use the way that hashing helps you to implement that is that you can take the key, you can hash the key, and use the number you get back from the hashing to determine the location. All right, so you have some keys, you have some values, and you have some big storage array, some big thing where you can store things, and you have different locations in that storage to store things. So what hashing does, if you take the key and hash it, that tells you where the data is stored. And then you can immediately jump to the location and find it without having to scan through all the locations to find the value you're looking for. So this example here it's like a table of 1,000 entries. Some of them are blank. So this is a hash table that has it starts off being blank, but then you start adding things, adding key value pairs, and you use the key you hash the key to give you a number, and that number corresponds to the location where it's going to be stored. And then in that location, you store the value, the key and the value. So like John Smith might be hashed to 873, and so you store John Smith here and the phone number, which was the record. This other person, Lisa Smith, so that is a different input, so it would be hashed probably to a different number. And so that means that there's a different location that will be used to store Lisa Smith. So in this hash table, you can quickly find elements. Even though there are 1,000 entries here, you don't have to look through all 1,000 to find something if you know what the key is for it. You just hash the key, that gives you a number, and use that number. You know that the number corresponds to the location. Okay, so this is like an alternative to those trees we talked about for indexing. The problem here is that there's actually a possibility of collision, meaning that you have two keys that hash the same value, especially because I know on the terminal, like that command line thing I showed you, the output was really long, that hash value was really long. But if we would take that, and if we want to limit it to a small range because we only have a small number of locations we're using, then the collisions become much more common. Like if we were using this MD5 hash function and only using the bottom 2 digits to figure out what location of storage we're using, that would work, except it would be pretty common that we would have 2 inputs that would have the same last 2 digits, although maybe it would be unlikely that the whole sequence was the same. All right, so you sometimes have collisions. In that case, you can like store a list of elements here, or you can use the next location, or you can hash it again. There are various strategies to deal with collision. That's kind of beyond the scope of this class, but the basic idea here, so this is a hash table. It's designed to store things in a way that you can quickly find records, and it distributes the records by hashing the keys of all the records, and the hash tells you the location. Okay, and because the hash function is sort of pseudo-random, it'll distribute the inputs in all different locations. And with a real hash table, you'd also keep track of like how many collisions there tend to be, how many elements are in there. Like once it gets full, you might expand the size to be twice as big, and then you'd rehash it, and that would reduce collisions. So you can have a hash table like whose size changes over time depending on how many elements are in there. But that's more like sort of advanced CS214 stuff. Okay. So hashes can be used as an alternative to trees to index tables. I've kind of just shown that. It lets you in one step find. So remember, for indexes, the way I motivated this was that you had a table that had lots of records. You wanted to find the ones, a particular row very quickly, and that you did kind of like a traversal down this tree to find the node associated with the record, and that pointed directly to the location. So similarly with a hash-based index, you can take a key, hash it, and that tells you the location. Although there could be a collision, so you might have to check a few entries, but it's generally pretty quick. Okay, so hash table makes sense. You have a table for storing things. You hash the key of the record, so it's just like the records are keys and values. The key is the thing that's hashed. That tells you the location, and then you store the value as well. All right, so how does that help us with distributed databases? It turns out that a hash table can be distributed very easily. So if you're storing things in a hash table, you can actually kind of you can use a different machine for the different ranges of the hash table, and that allows you to very easily distribute data across many different machines and to very quickly determine which of many machines is storing the data that you're looking for. If all you're storing is a big hash table, it's big because it requires many different machines to store the data. You can compute the hash of the key, and that gives you a number. And then if you know that there are 3 different nodes in this cluster, and that the first node is handling the first third of the numbers, the second one the middle numbers, and the last one the last third of the numbers, you know not just the location of the data in the table, but also the particular node that is storing that part of the table. Okay, does that make sense? All right, so a NoSQL database. You guys heard the term NoSQL? So NoSQL databases are kind of popular. It's a hot term in technology, and so these are databases that don't use SQL. All right, so. So we'll learn in this lecture what they're useful for and what they're not useful for. Well, we're not actually going to use them in the class. But NoSQL databases basically are just distributed key value stores. So they're basically just this idea here. Distributed hash table across many different machines is what a NoSQL database generally is. So it's one big table with a primary key. And because they are just big hash tables, they have the interface for getting data for storing data and retrieving data is not the SQL language. It's just getting and setting values, getting and putting values using a key. So it's like one big table, not many tables, and there's one primary key, and you always use that key to find data and to set data. Okay, so it's like a much simpler design, but it's less flexible and less powerful than SQL because you can't have many tables, you can't have foreign keys, you can't index on many different columns, things like that. But it's so by making the design a lot simpler, by just having one table and just having one primary key, and that's it, that allows these designs to be very scalable because they can use this kind of scheme here, where hashing is used to determine which node is storing the data. And then you just get that data from that node, but it doesn't support queries that operate across the whole data set very well, or retrieving data according to other column values and whatnot. Because if you do anything other than just get a single value using the primary key, then you have to involve all the nodes in the database, and that becomes very slow. And you have to transfer a lot of data between nodes in the database, and that also becomes slow. Okay. So that's NoSQL. So if you have a NoSQL database, because it's a distributed hash table down here, representing it with a cylinder, because cylinders are often used to represent storage in databases because magnetic disks kind of spin around. I think that's why they're cylinders. Anyway, so you have many different computers here storing the data, and it's a distributed hash table. You can get and set values. And because there are many nodes there, it can support many different analyses happening in parallel in a much better way than a single database. But the kinds of queries they can do are much dumber. It's just like getting values using a primary key or setting values using a primary key. I mean, you can potentially do scans, and there's some SQL-like languages built on top of that, but they tend to be really slow because they have to be at a lower level implemented using the sort of get and put semantics on a single table. Yeah. Any questions about that? NoSQL? Yeah. So another, because I mentioned already that NoSQL databases can have a lot of nodes, and therefore failures are more likely. So fault tolerance is kind of built into the software, so that the database is designed to allow one of the nodes to die at any time and still carry on. So data is, I mentioned before that the distributed hash table tells you or the hash function tells you what location the data is stored in. In reality, you might apply like you might apply 3 different hash functions to figure out 3 different locations, or you might have a rule that tells you that you store it in one location plus the 2 bordering locations, so that you store any one data in 3 different locations. And the reason for that is because crashes are common, or more common anyway. So therefore, if you store a value 3 times, then not only is it less likely to go away, to be lost, but also if you only hear back from 2 out of 3, then you can be pretty confident that the third one would have said the same. Or if you hear back 3 responses and 2 are different than the third, you can use the majority vote to decide which one to use. And the reason why there might be differences is because if you're dealing with a database that's changing over time, there could be a write which modifies data around the same time that you're doing a read. And so those changes could be partially made at the time that you're checking the data. And so you have to have some way to deal with inconsistency. And so consistency is a big kind of nuisance with NoSQL databases, but there are ways to deal with it. On the other hand, traditional SQL databases tend to be one computer, and then they have redundancy at the hardware level, like multiple power supplies, multiple fans, multiple disks working together, storing data, battery backup, stuff like that. So you tend to use a more expensive server to host a traditional SQL database, because if it fails, then the whole database is unavailable. Whereas with a NoSQL database, they're kind of designed to tolerate the failure of one of the machines and still carry on because you have replicas of data and so forth. Okay. All right. So yeah, that was a quick introduction to NoSQL databases, distributed hash tables. So that now you have you've seen 2 different tools for dealing with data, and we haven't seen in much detail NoSQL databases, but one of them is more capable of handling larger data sets because it can handle has a natural way to deal with many computers. It uses a hash table to decide where data is, a hash function to decide where data is stored. And the beauty of that is that if you're requesting data, you don't have to ask anyone where the data is stored. You can just do the calculation of the hash yourself, and that tells you which node you need to ask for the data. But there are a lot of variations in data processing tasks, not just the size, but other things. And today I'm going to focus a little more on different sizes of data and how to deal with them with different tools. And excuse me. People talk a lot about big data. In order to understand that, I find it useful personally to introduce the idea of little and medium data. To understand what's not big data, you need to understand, and there are actually 2 other distinct classes of problems that are not big data problems, and I call those medium little data problems. Excuse me. All right, so what we've been dealing with so far in class are medium data tools. Okay, so the SQL databases are a medium data tool. So it's different than what you learned in your intro to programming class are a bunch of little data tools. So if you write programs in a traditional programming language, you are working with the memory in that computer. Memory is limited to 8 gigabytes on a really good laptop or a decent laptop, or perhaps up to 1.5 terabytes on a good server, but it's limited. So when you declare variables, arrays, dictionaries, lists, and all that stuff, that's all in memory, and that's limited, right? Databases allow you to do analysis of data, not using program variables and stuff, but it's using a database that somehow the database management system uses the file system of the computer, so it uses the disk to store data, and this allows you to store a lot more data, and you as a user don't have to worry about transferring data between disk and variables and stuff like that. So you can solve problems that are much bigger. So this is 100 times bigger, maybe 50 times bigger. And it actually can scale even beyond this. So on your laptop, you probably have 256 terabytes of data. So even just on your, I'm sorry, this should have said gigabytes. Should be a G. There are actually very few data sets that are more than 200 gigabytes. So you can do a lot of analyses, even analyses that people think are big data analyses on one computer, even a pretty modest computer, and using tools that can run on that one computer, such as a SQL database, right? But there are some problems nowadays that require you to use multiple computers. So this picture here shows a computer cluster. So these are like every little. These are racks of computers and thousands of computers connected together. Once you start connecting computers together, capacity is basically unlimited. And this is useful when you have tens of terabytes or like petabytes, exabytes of data. No one really, I think only Google has exabytes of data. Question?
I was gonna ask what types of problems true big data.
So there's no like quick answer, except I would say, by my definition, a big data problem is one that requires using something other than SQL, like something bigger than SQL, which means multiple computers, something like Hadoop. We'll talk about that in this second half of the lecture. But you can start off by looking at the size of the data. So this is like a rule of thumb. Like if your data can fit on your laptop, then it's hard to argue that it's a big data problem. If it can't fit in your laptop, maybe it can fit on like one of the servers that's in your business. And maybe it's still not really a big data problem, but it's like a problem that requires that you can attack with a SQL database to do the analysis. So the size of the data is important, and also the type of analysis you're doing, and the amount of time you can afford to wait before getting an answer, and also the nature of the data itself. If it's all like numbers and stuff that's easily stored in a database, if you have like image files, things like that, then you can't really use SQL to look for things in image files. You need some other tools, and then like something like Hadoop could be useful in parallelizing, for example, image processing, things like that. All right, but size is definitely an important aspect, and I like to think, and again, like what fits in memory, it can use like a lot of different tools, very simple tools, like just a basic programming language without even using files. If you can fit it in one computer, in the disk of one computer, you can use it in you can use a SQL database, and that gives you a lot of more. It's easy to do SQL analysis, as we've seen. Those queries are pretty simple, even if you're operating on data that's on disk, that's quite large, right? But if you need to go bigger than that, there are other tools available. Okay. So when I talk about little data tools, this is like MATLAB is definitely one, because like all those arrays and matrices that you define in MATLAB, those are all in the memory of the computer, and you can't make them bigger than the memory that you have in the computer. You can use virtual memory with swapping, but that gets to be really slow, and so basically you're limited to the size of the memory in your computer. When I say memory, I mean the RAM. Like I said, it's maybe 16 gigabytes. When you're using a general purpose programming language, if you're just using the basic stuff built into the language, like the arrays and dictionaries and lists and variables, that all has to fit into memory. So that is kind of, in some sense, those are little data tools, although you do use those general purpose programming languages with the medium and big data tools as well. So you can access files with these languages, and that gives you access to more data than it can fit in memory. But accessing files is not really native to those languages. It's not really built into the language. You can't do an addition or subtraction on data that's on disk directly with any of these general purpose programming languages. You have to like open a file, copy it to an array, do something, write it back to the file. All that opening, copying, and writing back, that gets to be really tedious. And like so when you do have data that needs to be on disk, moving to a SQL database is really helpful because it manages the shepherding of data between disk and memory automatically. So that lets you essentially read stuff on disk, change stuff on disk without having to worry about opening files and things like that. Okay. Excel is another little data tool. The spreadsheet's saved to a file, but when you open it up, it has to all fit in RAM. So like for the project, if you're working on big data sets, you'll find that Excel gets really slow because it has to fit everything in memory when it's working. Okay. All right. So most of this class has been dedicated to giving you tools to work with bigger data sets, which I would call medium data sets. And SQL relational databases are the most useful tool in this domain. And these allow you to create tables, define indexes, load data, write queries. And you don't, somehow, like, you don't have to worry about the fact that the data is on disk. You can just access it directly, and the database management system handles the details. It pulls the data from disk into memory, because actually the computer itself can only really operate on data that's in memory. So there does have to be some transfer between disk and memory, but you don't do that yourself. When you're writing queries, you don't worry about that, right? And so you can combine SQL relational databases with general purpose programming tools and other analysis tools, so like MATLAB, Python, and R. Those all can use a SQL database to do analyses that include to have all the power of a general purpose programming language, and all the statistical packages built into some of these tools, but which also are able to get data from disk using queries, which is kind of easy, right? Pretty easy. But aside from SQL databases, there are other ways to deal with data on files, in files, I should say. And just quickly, so one basic, this is like when you're building programs from scratch to deal with data on files. One common way to deal with it, if those files are too big to just load all into memory, like if you're writing a program that works with a file, you're not necessarily doing a medium data analysis. You could be doing a little data analysis. If you load the whole file into memory, then that's little data, right? Everything's in memory, and that's easy to do that. But if you have really big files, you can try to do some kind of streaming where you open a file and you read pieces of it and you do something with it and you close that and you move on to the next piece of the file. And that can work, and that allows you to not use a lot of memory. You just are looking at small pieces of the file and moving on. You're scanning through the file. If you're looking for the largest value in a data set, it's very easy to do that. A simple aggregation by scanning. The grep command line tool is a regular expression search tool for text that does that. It opens a file, scans through it, looks for patterns. You can also organize your files into different folders and file names that tell you something about the data. For example, if you have data that applies to different years, you could have a different folder for each year that you have data for, and so there, you can navigate through the folders to somehow find the data you're interested in. And there's a tool called SAS that is a statistical analysis package that actually works really well with large data sets, but it's kind of equivalent to a SQL database in the way that it works. Anyway, those are just some other medium data approaches. So you're working with data without loading the whole thing in memory. And you also can apply relational databases to some pretty big data sets. So a single computer with one disk might only have about 12 terabytes of data of capacity. Well, I say only 12 terabytes, but it's actually pretty big, right? It's rare to find a data set larger than 12 terabytes. Like that Stack Overflow one was 150 gigabytes, so 1/10 the size, basically. But anyway, it's possible. And there's limited throughput, so a disk can only transfer a certain amount of data per second, 150 megabytes roughly. But even with that limitation, you can still build medium data tools that are more powerful than that by connecting lots of disks to a single computer. I showed you this picture before of a big database server at Northwestern at Kellogg, and this one had hundreds of disks, and those are called RAID storage arrays when you combine multiple disks. So you have a database management system running on one machine. That machine might have more than one CPU, has some memory, and then it has a connection to lots of disks that store data, lots of data, and it gives you a lot of capacity. There's limited bandwidth between the CPU and memory and the storage, so you can't really access everything at once very quickly. But this kind of architecture allows you to tackle some pretty big data in quotes problems, some pretty big data problems. But these are using medium data tools. So these are traditional tools, traditional hardware designs. But this is capable of scaling to really quite big data sets, like hundreds of terabytes, which is much larger than I think most of you will ever see in your early career until later on. Eventually, of course, data is getting bigger and bigger as the years progress. So medium data tools. The things you're learning in this class are pretty scalable as long as you have like an IT team that knows how to build like big database servers for you, and they'll actually do that for you. And when you go to a company that has databases, typically they have big databases that look like this, like big machines with lots of disks connected to them. They'll let you do analysis on them, and using the tools you've learned in this class, although those are not big data tools in the terminology of that you'll see about like in the news and whatnot. So even like a really big online store, like the Amazon store, I think all their products are stored in a SQL database, although they do have some information that's stored in a NoSQL database, like the shopping carts that all their users build are stored in a NoSQL database, but the actual product information is in a SQL database because there are a lot more shopping carts created than there are individual products. And the shopping carts are modified a lot, whereas the products themselves are mostly just read. They're not written. Mostly just read, not written. So, SQL databases are pretty scalable. And there are some cases when you need to work faster and support more simultaneous analyses, and that's where big data tools are useful. But don't jump to using... I think you make a lot of use of the SQL tools you've learned in this class before jumping to other stuff. Okay. Yeah. So, I mean, theoretically, I have a little calculation here. Well, a modern computer can actually transfer about 80 gigabytes per second of data from disk, which is a lot. So even if you have a huge data set, like 10 petabytes of data, 10 petabytes of data is like massive. That's like, I'm not sure how to even, that might be like a good chunk of all the YouTube videos that are stored, something like that. And even on one computer, theoretically, you could scan through all of them in maybe 3.5 hours if you have a storage system, if you have a lot of disks connected to it, so you can do parallel operations. But again, you still may find a situation where you try to use a SQL database and it's just too slow, and you decide you want to go to parallelize it, and so you want to jump to big data tools, and that's where distributed computing, big data tools come in. Okay, so in distributed computing is you hear a lot of different names for the same technologies. Parallel computing, distributed computing. Parallel computing usually refers to like scientific computing, where it's mostly computation, that it's mostly CPU heavy work, and there's not a lot of interaction with data necessarily. And the data system is separated from the compute system. But with distributed computing, that term generally means you have a bunch of computers that have both data and compute capacity, and they all kind of work together somehow to do an analysis, and they all can communicate with each other. And so no one machine has direct access to all the data because the data is too big to fit in one machine. Instead, each computer has a slice of the data. So this could be sort of like, this is similar to like the distributed hash table, right? And you want to get some work done, and so somehow these computers need to all coordinate to do the work, right? So this is like motivating Hadoop, basically. So if you have a problem like you want to find the largest sales order in a database, some huge database. The database is so huge that it's distributed across all these computers, and like each computer stores a different month of data, let's say, just to simplify things. Like, February orders are here, March, April, May, June, and so on. And you want to find the largest order among all of them, then it's pretty easy to see how you can distribute the work, right? Because the maximum of the overall system is going to be the maximum of all the maximums, right? So you can come up with some program that you want to execute in this this master node, which is what you're controlling as a user. You distribute a computer. you distribute that program to all the nodes so that they know what is going to happen. They have a copy of the analysis to run. They have some instructions. And then the next step would be, in this case, for each of these nodes to compute its own maximum. So it could be that, for example, the biggest February order was $54,000, biggest March order was $10,000, and so on, right? They each can do a piece of the work, which is to compute the maximum over their chunk of data. They can send the results back to a single node, which is up here, the master node, right? So these are all the maxima from down here. And then this node can just scan through them, and that would be very quick because there's only a small number of, maybe a few hundred nodes at most to find the maximum overall, which in this case was 54,321 from February, right? So that was like a trivially parallelizable problem, right? So, but we somehow had to figure out how to distribute work and how to define the problem in a way that it can be computed in parallel. And that's difficult in general. I mean, for this particular example, there's a pretty simple solution. But you need some kind of a platform to do that parallel computation. And Hadoop is an example of a popular distributed computing platform, which it manages both the storage of data on a cluster and also the running analyses on those clusters, on a cluster. So the two main components are, the storage and the compute, I guess, are these two things. Right, so the storage is handled by HDFS, which means the Hadoop distributed file system. So there's a file system for storing data across all the different nodes in the cluster. It looks like a regular file system with folders and files and whatnot, but somehow those are shared across all the nodes. You can think of it as being implemented probably with some kind of distributed hash table. And there also is a programming model called MapReduce, which lets you define your analysis in a way that makes parallelization easy for the system. Okay, so you would usually use Java, but you could also use some other languages to write your analysis. So this is different than like just running a SQL query, which is usually pretty short. This involves writing usually at least a few dozen lines of code to say to specify your analysis. So your analysis is like a program in maybe Java, but it uses MapReduce. We'll see what that means later. So basically, you have to define two operations, map and reduce, and those two things together should somehow do your calculation. And because of the nature of map and reduce, they can be distributed on many computers to do the work. Okay. This is based on a 2004 Google project, and there's an article that describes it. But Hadoop itself is an open source project based on that. So MapReduce, what is MapReduce? Okay, so it's like MapReduce is a way of taking a task and breaking it into two steps, a mapping step and a reduced step. And each of those happens in parallel. There are many maps that happen. There are many reduces that happen, but it happens in like two stages. So you have some input. Sorry if it's blurry here, but your map, you write some code for map that takes an input and produces a bunch of outputs. And that is run on many different inputs, again, producing many outputs. And then all those outputs are run through reduce functions. And the reduce takes a bunch of those intermediate results that were output in the previous stage and produces one output. So it's like you compute some stuff, like many things, and then you take those many things and you reduce them in some way. And then, which is like it's a very general structure for a program. But then you actually write the code for the map and the reduce so that it implements what you're trying to solve, right? Yeah. So again, each of these map and reduce functions take key value pairs. So you have to define these map and reduce functions, and the map function takes in one key and one value. So this has one input, and it outputs a list of key and intermediate value pairs. And reduce will take those intermediate values for each of the keys and produce a list of outputs. And so it's a very abstract. These are two abstract functions that could do almost anything, kind of. But because it operates in two stages, and because these maps can happen, many of them at the same time, reduces can happen many of them at the same time, it can solve problems in parallel. So an example, I think it's a little bit hard to understand this without going through maybe more examples, which you don't really have time for. But one example is counting words. So if you want to count words in some large data sets in a Hadoop distributed file system, so it's in a cluster, and so this is a little bit more complicated than just finding the maximum, right? Counting words. So in this case, you can define a mapper that takes a piece of the input, which is some document, and it looks at every word and prints out. It outputs that word and the number 1. So it gives a 1 for every occurrence of the word, basically. So that's the mapper stage here. It takes a document and outputs a bunch of things. In this case, the output is a bunch of ones, a 1 for each word that it saw. Okay, that's the map step. And the reduce step, this is going to happen in stage 2, and all those maps happen at in parallel across the entire set of documents. Right, so you're going to end up with a bunch of words and ones associated with the words whenever they were seen. Reduce will take for each output key, which is equivalent to the W there, the word. It'll operate on a word and a list of intermediate values, which is a list of values or output. So it'll be a list of ones, and it basically adds up all of the intermediate values it sees for that word, which will be a bunch of ones and other outputs from reduce. So it'll sum them up and print it out, and that gives you a total of the number of words. So this diagram kind of shows how that works. So the map step is between the red and green here, and the reduce is in the blue. So if your output is this text here, welcome to Hadoop, class Hadoop is good, Hadoop is bad. It's just some text. That text is distributed across, is broken into pieces and given to a bunch of mappers. And remember, the mappers output a list of words along with the number 1 for the word when it's seen. Those are shuffled here to group the outputs that have the same key together. So, for example, Hadoop is output 3 different times, and that's combined here into 3 different entries for Hadoop, 1, and those are fed to one reducer that takes that, and based on the code I showed you, it adds up all the different ones to produce 3, and the output is this list of words and the number of occurrences. Okay. So as a programmer, you just have to write the mapping and the reducer, and this like shuffling and splitting of inputs, that's done automatically by the runtime system. And if you've thought carefully about your problem and you understand what map and reduce does, you should be able to break your problem into a map and a reduce that will somehow solve it. And this is just a little bit of code that could be run across a ton of computers to get the work done correctly. And keep in mind also, I think the reducers could happen in, you could even write this in such a way that the reduce worked on an intermediate result and emitted an intermediate result, so you could do partial summations of words that were fed back into the problem. Yep. All right. I know that was pretty quick, but does that map and reduce concept make sense at some level? I'm going to explain either of them anymore. So, maybe we can think about an example of a different problem. Like, let's say we wanted to compute the average sales order size. Right? How would you solve that with map and reduce? If you can think about that for a couple minutes. Average sales order with MapReduce. And assume that the inputs are a bunch of sales orders that just have like, it's a list of values of numeric totals. You want to somehow take those inputs will be distributed to a bunch of different maps. And those maps can produce whatever you want, some list of outputs, they're intermediate. And then you'll deal with them in your reduce function to somehow compute the average overall. Okay, so so you said you want the map to compute the average of some slice of the data. So what does it actually produce though? Like what? Just the average? Just the average would not be enough to aggregate it later, right? Because you don't, like, for example, the different mappers could get different slices of the data. Sorry. Like for example, yeah, like this one got 3 words, the next one got 3 words, the last one only got 1 word. So you have to, like you said, output the average and also the number that was in it, right? Yeah, so if the map outputs the average value as well as the number in that that contribute the weight of that average, kind of like the number of entries, then the reducer can take that and do a weighted average of those to produce another weighted average with some other number, and that could be an intermediate result that goes to yet another reducer. So actually, in that case, maybe the map and the reduce. Well, the map takes the input and turns it into this format where you have the weight and the average, or like the count and the average, and then the reducer can take a bunch of counts and averages and output a new count and average that is the sum of all the counts as well as the weighted average of those, right? And eventually, at the end, you should output something that is like the total count and the overall average, right? But that's a very simple analysis, but it's with this design, it can be scaled up to lots of nodes, which is cool. All right, so I've kind of already said this a few times, but beware of the hype around like Hadoop and big data and NoSQL. So Hadoop is designed for huge scale, but it's inherently slower than traditional approaches. There's like a paper here that has some tests that bear that out. Like it doesn't have, like SQL databases have a lot of nice features like indexes and query planning that cleverly orders things to do things efficiently. There's a lot of overhead here for creating these new map and reduce tasks and shuffling data between them. And you also need a special environment, like you need a Hadoop cluster, which you might not have. If you do have one of those in your work environment, obviously you can make use of it, but it's more common to find a SQL server. So I would say don't use Hadoop, MapReduce, or NoSQL unless you really need to. So if you know that your data is petabytes in size, then obviously that's one indication. So look at the size of your data. If it's petabytes, then consider using a big data tool. Or if you just know that the analyses are slow and you've already tried to do the normal things of adding indexes. So SQL queries can be much faster with indexes. We saw that in homework 5. Yeah. And so I would say that probably 75% of people using Hadoop and NoSQL don't really need to. And they're actively hurting themselves by using a tool that is too big. Because it's not just that the tool is too big, but like it has fewer features than the tool that's designed for smaller data sets. Like SQL has a lot of really nice features. The queries are easy to write. The indexing is fast. You can index to multiple columns. The foreign keys allow storage to be really efficient, things like that. All right, so to recap the discussion, we talked about NoSQL databases and Hadoop as big data solutions. We also talked a little bit about what medium and little data are. By the way, I invented those terms, medium and little data. Okay, so I think you should use them to impress your friends, but don't expect them to know what you're talking about. Okay, but I think it's a good way to structure the conversation about big data, because a lot of people aren't really clear about what they mean by big data. Okay, and how SQL fits into that. Because actually, I've seen a lot of people talk about big data research problems, and then the solution they applied is a SQL database, which is great, but the term big data kind of misleads people into thinking that maybe they're using different tools. And yeah, anyway, so hash functions are a useful concept that allow you to deterministically take an input and map it to some kind of pseudo-random output, which seems kind of weird at first, but it's actually quite useful for building storage structures that allow you to find the location of an entry very quickly without having to search through everything. You just hash a key that gives you a number, which ends up being the location. And NoSQL databases are distributed hash tables. So they're just a way to store a dictionary or one table with a primary key. They lack the full power of SQL, so you can't really write the same queries. You can't do joins and things like that. But they're a lot faster. They're a lot more scalable. They can handle much bigger data sets because you can kind of distribute across many computers very, very easily. Hadoop is a distributed computing platform that uses MapReduce, and you have to somehow figure out how to translate your problem into one that can be expressed in terms of maps and reduces. And for some simple problems like finding the average, finding the minimum, maximum, counting things up, it's quite easy to figure out how to do a map and reduce. But if you were to take an arbitrary SQL query, it might be more difficult for you to. It's possible for sure, but you have to think a little bit more about how to translate that into maps and reduces. And I would say overall, stop and think before using big data tools, because SQL is quite scalable, and learn how to use indexes. All right, thank you. See you on Thursday.